This is chapter 20, lecture number 1. Topic of this chapter is NOR and NAND latches. So this is really an important chapter because it represents a switch to another type of a circuit, and we'll get into that in a second. This chapter is very low level, so it's really hard to generate example problems for the material in this chapter. But we will have 1 or 2 problems there, and what we're going to do in later chapters is abstract this to a higher level, and once we do that we will have many more example problems. There's some other issues involved in latches also that's going to prevent us from making reasonable or useful circuits out of it. So new terminology here, there's essentially 4 things you can do with a bit. So here they are. You can do nothing, which means don't change the value. You can set it, you can clear it, and you can toggle it. Toggle it means inverting it. So if it's 1, it becomes a 0, and 0 becomes a 1. So this is always a very important question. You see it come up a lot, particularly with the new circuits we're going to get into. So 4 things you can do with a circuit: do nothing, set it, clear it, toggle it. Remember, clear it, just make it 0. Set it means make it a 1. So as it turns out, there are 2 types of digital circuits out there. Those are combinatorial circuits and sequential circuits. So essentially, everything we've been working with thus far has been combinatorial circuit. If you recall from those circuits, the outputs of combinatorial circuits are a function of the input. So it's a direct function of the input. So it's known that these circuits do not have memory. We haven't really dealt with the issue of memory, and thus, because they don't have memory, they don't have state. State is essentially a value that your circuit's memorizing. So we're now getting into sequential circuits. Now sequential circuits, the outputs aren't a function of the inputs, they're a function of the sequence of inputs. So it's a little bit differently, and so because of this, these circuits necessarily have memory, and because they have memory, they have what we refer to as state. Once again, state is simply what the circuit happens to be memorizing at any given moment. So once again, the state of a circuit is the values in that circuit's memory elements. These are our foundation modules that we've used up till now. These have been all combinatorial circuits. This is our first chapter with our first non-combinatorial circuits. Carry out, you can see them here. I'm not going to go over these, but some of these circuits have data in, data out, status out, and control in, depending on what circuit it is. We're now going to get into sequential circuits, so it's not that much different. And just keep in mind, these are 6 foundation modules. We're going to start adding a few more. There's only about 3 more to add, and then we're going to call it done. This is a new circuit, maybe. Looks like some NOR gates. Is it a question of, is it something we've seen before? It is a little bit unique because what we're doing is taking this output and feeding it back and using that output as an input. This is very significant. Once I do that, it's going to change this circuit into a sequential circuit. And remember, a sequential circuit is a circuit that has memory in it. So most importantly, the physical characteristic of a circuit that gives it the ability to memorize data is feedback. And so this is a really important word. It comes up multiple times there. Remember, it's feedback from the output to the input. So it's reusing the output as an input, and this is going to give the circuit some unique qualities that we'll see in a second. Here is the circuit we're looking at. What we're going to do is kind of model this a little bit differently, and what we're going to put in here is this box that we're going to call TD, which is essentially a lump delay. What I'm taking is the delay from these 2 elements, I'm putting in this box here. So the notion is we have the output of the circuit, and then we have the new output of the circuit, and the difference between them is a time difference. What we're going to look at is this is the current state of the circuit, and this is the new state of the circuit. Here's our little diagram here. What we have here is the circuit has 3 inputs that we're calling S and R. S and R and Q is being fed around here. So here's Q, S, and R here. And what we want to find out, it's just a normal circuit now, is how that affects Q+. Now Q+ is going to be the new state of the circuit. Typically we use Q to represent. I'm not going to do the whole thing, but I'll do a couple of rows in here, and then we will just flip to the next page that has all the answers on it. Okay, so let's do this. And first thing we need to do here is my truth table for NOR, and I'm going to use that in the analysis of this problem. What we have here, anytime there's a 1 on a NOR gate, the output's a 0, so we're going to take advantage of that. So here we are, we'll do this first row here. Q is a 0, so that's a 0. Everything's a 0. Okay, so S is a 0, 0. Okay, 0, 0 is a 1. I got a 1 on a NOR gate, the output's a 0. Okay, not too exciting. Okay, let's do this row right here. What we have here is Q is a 0, and S and R is a 1. So that makes this is 0, and this is 0. Okay, so in this case, we got a 0 so in there. And let's do one more here. Let's do this row. In this case, what we have is Q is a 0, S is a 1, R is a 0. So this is a 0. 1 makes this output a 0, 0 and 0. Looking at this is a 1, and this is a 1. I think we've done enough of those. Let's go up to the answer. This is the result of that analysis, and it should match what we saw before, at least in those 3 rows we did. And so what we're interested in is how Q changes when we get these inputs for S and R. So if you look at this, what we see here is there's no change there. That's why we call it a hold. If you looked at these two, what we could say is the output cleared. If you look at these two, you can say the output always set. And for what we're going to do is call these forbidden states, and then we'll say we can't do those. So what we have is circuit has the ability to hold, clear, or set. It's very important. It doesn't have the ability to toggle, but it can do the 3 or the 4 things you can do with a bit. Now this is a compressed truth table. This is a topic we used to delve into in older approaches to digital design, which we don't do anymore, but it's really kind of instructive. So if these are the 2 inputs, the output is going, this new output here is going to be the same as the old output, which describes a hold. So the set and clear, these are the set and clears right here. These are the conditions that give me a clear. These are conditions that give me a set. Okay, we'll see those coming up in a timing diagram in a bit. So here's your timing diagram. This is my compressed truth table. We can see that when S in this row right here, and when S and R is a 0, the output holds. And so that's what we're seeing right here. S and R both 0. Q has to be given to you. Q is the state of the circuit. And here we go, at this point right here, S becomes a 1, R is a 0. Here we go, S is a 1, R is a 0. That is the set state that causes the Q value to go to a 1. So the cool thing here is at this point right here, the S goes back to 0, which means the input's 0 and 0, which is the hold condition. That hold condition holds the state of the circuit. It's being held at this 1 value right here. So it was 1 when we decided to hold it. It remains being held in this little time slot right here. What I did was I set this, and then I decided to hold it. So what officially it's doing, it's memorizing that first bit I set. Then lastly, I can also clear this circuit. Here's S is a 0 and R is a 1. Okay, S is a 0, R is a 1. That's the clear condition. Here's your clear happening right there. The output goes to 0, which is the state, and then I can switch it back to the hold condition. And by all means, that 0 doesn't magically change to 1. So in the circuit, the way I get this output to change to 1, I set it. The way I get the output to change to 0, I clear it. If I want to hold the output, I hit the hold condition, which is S and R equals 0, 0. So roughly speaking, S equals set and R equals reset. So that was this circuit. So this Q output here is the state of the circuit. It's a value that's being memorized. Remember, state is essentially the value that's being memorized by a given circuit. This little circuit we had before has the ability to memorize a single bit. So it is officially, this is the circuit we analyzed. It is officially a NOR latch. There's your NOR latch, cross-coupled NOR cell, or cross-coupled cell. This is the original circuit. If I tweak this around, bend it around, I can make it look like this. This is this classic cross-coupled circuit, which is interesting to look at. We've actually put this Q bar here. And lastly, I actually can use a black box diagram for this. Now the issue here in this black box diagram is the output of NOR cells, or cross-coupled cells, have complementary outputs. So here we have Q and here we have Q bar. This is probably actually not the best way to draw this thing. It should have been written like this. They're both Q outputs. One's positive logic and one's negative logic. Maybe a better way to draw this thing. This circuit, little circuit here, has feedback. The feedback gave it the ability to memorize a single bit, and we're going to call this a bunch of different names. It usually goes by latch. If you need more information, it's a NOR latch. So state diagrams, it's a super important way to model sequential circuits. Essentially, as the name implies, it's a state. It models the state. It shows the different states of the circuit. This is going to be a quick introduction, and we're not going to go too far with this. We'll hit it again later. And so this is for this state machine. What I want to do is draw the states. So this is somewhat arbitrary. I can make Q equals 1 up here and Q equals 0 down there. It doesn't really matter. But what I need to do is represent these state transitions. So there's the states. It's a 1-bit storage element. It's memorizing 1 bit. Here's a 0 to 0 transition, and I'm going to represent that with an arrow. And the conditions on this transition there are S bar, R bar. And I'm going to do that for every row in this table. Here's a 1 to 1 transition. So it starts in state 1 and it goes to state 1. The conditions are S bar and R bar for that transition also. So we'll keep going on this thing. Here's a 0 0 transition. We already have that transition. So this is going to be S R. Okay, and here is a 1 to 0 transition. 1 to 0. The conditions are S equals 0, R equals 1. Here's a 0 to 1 transition. The conditions are S, R. Here's a 1 to 1 transition. The S, this is an S, R bar. And I think since these are forbidden, I'm not going to put them in there, and we can almost call this done, although we can factor this thing. This is R times S plus S, which equals R bar. This is S bar times R plus R bar, which equals S bar. And so we can, once again, we get simplified those a little bit. And so that's our state diagram. Once again, we're going to be doing this with primarily the rest of the course. This is a super brief intro. And what we did here was we transferred the information from this table into this diagram. Now this is hard to read. This table has a lot of 1s and 0s in it. It's really tough to read. State diagram's much easier to read because they're kind of a visual description of the circuit rather than a tabular description. So these are the two diagrams. This is essentially the diagram we ended up with. These are the two forbidden states that we just opted not to put in there. We did put the verbal description of what those conditions are doing for this state diagram in this diagram, but we ended up with this, which is a state diagram. Once again, it's a 1-bit storage element. That bit can either be a 0 or a 1, and that's what we've represented in this state diagram. That is a NOR latch. We've seen all these diagrams right here. What we also have out there are NAND latches. You could go through the same analysis on this thing. What we have here is the difference being is this. I mean, these circuits look pretty much the same, but the difference being for a NAND latch, the inputs are essentially active low when compared to the inputs of the NOR latch. So essentially the 1 1, when S is a 1, R is a 1, that is the hold state for this circuit, while for the NOR latch, when S was a 0 and R was 0, that was the hold state. Very much the same, difference being the S and R are active low inputs. So this is our summary of important stuff that are in this chapter. This is our first introduction to sequential circuits. Everything up to now has been combinatorial, which means combinatorial circuits didn't have the ability to memorize anything, thus they had no state. Now our sequential circuits can memorize stuff, so we talk about them as having state. But we talked about 1-bit storage elements, which were latches. We talked about both NOR and NAND latches. Primarily, we did most of our work with NOR latches. So the word latch is very important because it represents two things depending upon context. So if you use latch as a noun, that is a storage element, particularly a 1-bit storage element. If I use it as a verb, as in to latch something, that means it's the act of storing data into memory. So this is very important. It's vernacular that we use all the time, and you'll absolutely have to get used to it. So lastly, we'll do a one circuit example here. Like I said, these are tough to generate problems for because they are low level, and we want to stay up at a high level here. So this is design a NOR latch that essentially only works properly when a button is pressed. And so what we want to do is we want to keep this NOR latch at the center of our circuit, and we'll just put it like this. I guess we should draw the diagram. It has an S and an R and a button, and we have a Q and a Q bar on this thing. This is the high-level black box diagram, which I think that's good enough. I think I'm going to erase it. The circuit calls out for a NOR latch. Here's my NOR latch. What I'm interested in is being able to have the button allow this to work or not. So that means when the button is pressed, that means it acts like a NOR latch. When the button is not pressed, that means nothing changes in the circuit. So it's a pretty straightforward solution to this thing. I got S and R. You've seen this one before, in that the button controls the input to these two AND gates here. So if the button's not pressed, the output of these two gates are 0. If the button is pressed, it allows S to appear here and R to appear there, and it acts like a normal latch at that point. And I think that's the whole circuit right there. It's kind of a little trick. You've seen this before. It's really common. Get used to it.